Today we're going to extend our knowledge of derivatives to look at related rates. So related rates are when you're relating the rate of change or the derivative of two variables. And a lot of things in society, when one thing changes, the other rate also changes. There are 6 steps that we will follow as we solve these related rate problems. Step 1, you should draw a picture. It's always good to visualize what's going on in the situation and carefully label your variables and your picture. Step 2, we need to write down what we know, what information was given to us in the problem. Usually that's a related rate. Then we need to write down what we're looking for. So what derivative or what rate are we looking for? Step 4, we're going to write an equation that relates the known variable with the unknown variable. Step 5, we're going to differentiate that equation so we can get the derivatives or the rates of change. And we're always going to differentiate with respect to time. So that means we're going to have to use implicit differentiation because our independent variable is time, not x and not y. Last step, we're just going to evaluate and solve. So here's our first example. We have a ladder that is 10 feet long, is resting against a wall. If the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second, how fast is the top of the ladder moving down when the bottom of the ladder is 8 feet from the wall? Step 1. Let's draw a picture that's representing a wall with a ladder leaning against it, and this ladder needs to be 10 feet long. Okay, these are the 2 rates of change. The ladder is sliding away from the wall, and the ladder is sliding down the wall. So that's the 2 rates of change that we're looking at. So let x be the distance from the bottom of the ladder to the wall. And I'm going to let y represent the distance from the top of the ladder to the ground. Notice it's very important in the drawing of the picture that I don't only just draw what the picture looks like, I also define what my variables will be if they're not traditionally used variables. Like we don't have to define r for radius because r is always used for radius. But any other variables like here, x and y, the length of that line, those are not traditional. They could have been anything. So I had to define my x and my y variable. So step 1 was to draw a picture. Step 2 is to write down any known information. So reading the given information, I know that the ladder is sliding away from the wall at a rate of 1 foot per second. So I have to translate that into calculus talk. So the rate of change of the ladder's distance from the wall, so that's the derivative of x with respect to time, is 1 foot per second. Always remember your units of measurement. Step 3, what do we need to find out? What are we trying to figure out in this problem? So what are we looking for in this problem? So I look up into the question. It asks us how fast is the top of the ladder moving down from the bottom of the ladder as 8 feet from the wall. So how fast is the top of the ladder moving down? So the distance, since y equals the distance from the top of the ladder to the ground, I want to know the rate in which y is changing. So dy dt, derivative of y with respect to time, is what I'm looking for. Now, what instance in time am I trying to figure this out? Well, I'm trying to figure it out at the instant that the bottom of the ladder is 8 feet from the wall. So I'm trying to do this when x is equal to 8. Step 4, we need to find an equation that relates my 2 variables x and y together. Since I know the derivative of x and I need to figure out the derivative of y, I need an equation that relates x to y together. This is where the picture comes in very handy. Since I have a right triangle, I'm going to use Pythagorean theorem to relate x and y. So I have x squared plus y squared is equal to 10 squared. I ran out of room on the other page, so I just go ahead and I put the most important information up here. Our known information is derivative of y with respect to time is 1 foot per second. We were going to find the derivative of y with respect to t when x is 8 feet. And we know our equation is x squared plus y squared is equal to 10 squared. So let's move on to step 5. Step 5 is differentiate the equation. So we're going to differentiate with respect to time. Derivative of x squared is 2x dx dt plus 2y dy dt. please do not forget the implicit differentiation. So since I'm trying to find dy dt, let's go ahead and solve this equation and get dy on the side by itself. I'll start by subtracting the 2x dx dt from each side of the problem. Next, let's divide by 2y. Simplifying the right-hand side of the equation, I end up with the derivative of y with respect to time is equal to negative x over y times dx dt. Notice that this equation has two variables, x and y, but I was only given the x incident when this occurs. So I was given that I want to figure this out when x is 8, but I need to know the y when x is 8. So to figure out the y value, so I can plug it into my differential equation here, I need to go back to the relationship, the equation where I related x and y together. And that was that Pythagorean theorem equation, x squared plus y squared is equal to 10 squared. And when I use this equation, I'm going to replace the x with 8 squared and then solve for y so I can get the y value when x is 8. As you can see from our work in blue, when x is 8, my y is 6. So I'm going to go to my differential equation, replace every y with 6 and every x with 8. And let's replace the dx dt with 1, since we know that was given to us. So derivative of y with respect to time at the instant where x is 8 and y is 6 is equal to negative, because I forgot my negative sign, negative 8/6, which is negative 4/3. Now in this situation, you need to know what negative means. Now dy dx stands for the rate of change of y. Remember, y is the distance the top of the letter is from the ground as time, with respect to time. Now the negative just tells us that the letter is falling down, it's going down. So when I translate my answer, because my answer is negative 4/3 feet per second, I need to translate this negative to what it means in words. So we always write our answer to word problems as a sentence. Since we're asked to find how fast the top of the ladder moves down when the bottom of the ladder is 8 feet from the wall, let's translate our answer to the ladder is sliding down, and that down takes care of the negative here. So when I write my number, I'm not going to use a negative. Down the wall at a rate of 4/3 feet per second. Make sure you use your units of measurement. So the ladder is sliding down the wall at a rate of 4/3 feet per second when the bottom of the ladder is 8 feet from the wall. Make sure you specify when the rate of change is 4/3 feet per second, because it does change. Okay, for our second problem, I'm going to look at an inflating balloon. So we're blowing up a balloon, and we're pumping air into this spherical balloon at a rate of 4.5 cubic inches per second. We want to figure out the rate of change of the radius when the radius is 2 inches. So again, first step, draw a picture. And here's my wonderful drawing skills. There's my balloon, and I have a radius. Notice I don't have to define r this time because r is always standing for radius. So step 2, what do I know? Well, I was given that we're pumping air into the balloon at a rate of 4.5 cubic inches per second. So filling up the balloon, that's volume. And this is the rate in which the volume is changing. So I would identify this as the derivative of v with respect to time is equal to 4.5 cubic inches per second. Don't forget your units of measurement. Okay, what are we trying to figure out in this problem? We want to find the rate of change of the radius. So the rate in which the radius is changing is derivative of r with respect to time is what we need to figure out. And we want to figure this out at the instant. We want to figure out the instant when r is equal to 2 inches. So picture what I know, what I need to know. Now I'm looking at the variable v and the variable r. So I need to come up with some equation that relates volume with radius involving a sphere balloon, something in a sphere shape. So I have to remember my volume of a sphere, is volume is equal to 4/3 pi r cubed. And this relates my volume with my radius. Step 5, differentiate the equation with respect to time. So derivative of v is 1 times my derivative of v with respect to time. Let's bring the constant 4/3 pi out, and the derivative of r cubed is 3r squared times by the derivative of r with respect to time. Don't forget the implicit differentiation. Since I'm trying to find dr dt, let's rewrite this equation and solve for the derivative of r with respect to time. So getting dr dt by itself, I'm going to divide each side by 4 pi r squared. And now let's substitute in what we know and what we need to figure out. Well, I want to figure this out when r is equal to 2. Now r is my only variable in my equation, so I don't have to find any other value, so I can just plug it straight into my differential equation here. And I was given the derivative of v with respect to time is 4.5. Simplifying this down, and since I had a decimal in my original problem, it's okay to write my answer as a decimal here. Usually go to 3 decimal places, but because this one rounds up, we'll only write it as a 2 decimal place. So I'm going to write it at 0.09, and then I need to check my units and measurements. So it's dr divided by t. So my radius is in units of inches, my time is in units of seconds. So that makes my rate of change for the dr dt to be inches per second. All right, let's translate this into a sentence. Okay, the radius is, and then I notice this is a positive value. So a positive value means that the balloon size is increasing. The radius will be increasing. So the radius is increasing at a rate of 0.09 inches per second. And specify when this occurs, when the radius of the balloon is 2 inches.